In this video, we are going to look at a little bit more at the relationship between fields and potentials. So let me remind you of something we saw a few videos ago. Let me take two parallel plates, and on one I'm going to put some positive Q, on the other I'm going to put some negative Q, and we're going to assume these are conducting plates, so the charge distributes itself uniformly over these two. And we saw what the electric field looked like between the plates. As long as I stay away from the edges, and as long as I make the assumption that this distance is much smaller, then I'm able to draw it and have this diagram make sense, right? We know that at the end I'm going to get these edge effects, but as long as I stay away from the edge, these edges, then I get this lovely uniform field, uniform in magnitude and direction. And then at some point I drew in some lines. Right? 1, 2, 3, 4. Let's say that I hold this at 0 volts. Remember, this is my reference point. I arbitrarily assign this point to be 0, and then I reference everything. If we're using our gravity analogy, this is the bottom of the hill, and up the hill here, we'll say this is 4 volts, right? So now we know in this particular situation, as I move to the right, I walk down, this would be 3 volts, 2 volts, and then the sign would be 1 volt, and then I would get back over here to 0 volts. What this means, because this field is uniform, is if I measure the potential between the points here and here, anywhere along this line, I get 3 volts. If I measure the potential between this plate and this point, I get 3 volts. This plate and this point, I get 3 volts. This plate and this point, I get 3 volts. If I measure the potential between these two lines, right, between the 2 volt line and the 3 volt line, well, you might imagine, because what I'm actually measuring is the difference in potential, I get 1 volt. But that is anywhere along the line. This point to this point, 1 volt. This point to this line, 1 point. This point to this point, 1 volt. This point to this point, 1 volt. That's the point. Anywhere along this line, I measure the same potential. We call these lines equipotential, right? From equal and potential. That is to say, these lines, these equipotential lines, any point on those lines is at the same potential. Equipotential lines. In this case, they're super easy to see and very easy to get some rules out of that. So let me first call your attention to, I'll abbreviate them like this. Equipotential lines are perpendicular to electric field lines everywhere. Now, in this situation, the electric field lines don't curve, so my equipotential lines don't curve. But if my field lines curve, I'm going to have to let the equipotential lines curve, and we'll see that in an example in just a second. But what this does is this allows you to graphically visualize the potential function. Remember, the field lines are there for us to get a graphical feel on what the electric field is doing. And now I can take it one step farther and visualize what the potential is doing. Let's look at the equipotential lines of a point charge. Right? We'll say it's a positive point charge. I know what the field lines look like. If I can bring myself to draw a straight line, possibly not. All right, we know what these field lines look like. They're everywhere radially away. Now, how do I draw equipotential lines that are perpendicular to these field lines? The only way I know of is to draw concentric circles. That was not a very good circle, but that's the idea. Right? And this actually matches up with what I know the potential of a point charge is. Potential of a point charge is KQ over R, right? Distance dependent in the first order. So each of these circles represents the same distance away from that charge. So if they're the same distance, the potential is the same. But the point is every one of these has a little right angle here, right? Of course, if you're a geometry Wizard, you understand that I mean perpendicular to a tangent line, the line tangent to that circle. But that's okay. I think you can see it regardless. Every one of these is going to be at a right angle. Those are the equipotential lines. Although I'm saying lines, this is a point charge sitting out in space would be three-dimensional, and these would be three-dimensional as well. They'd be concentric spheres, right? Not just concentric circles. So it's okay to say equipotential surfaces if you want to. I'm drawing it on paper, so I'll say equipotential lines, but that works. The surfaces works too. Let's see another example of a slightly more complicated system. So, and I'm not going to be able to draw this very well. I should point out a simple Google search will get you a much better drawing than I can get you. But let's look at this situation we've looked at before. We looked at it with the field lines, positive charge and negative charge, same magnitude. The name for this is an electric dipole. You don't necessarily have to know that for this course, but dipoles turn out to be pretty important, so might as well tell you their name. And the field looks something like this. I guess I don't really need to. Yeah, there you go. All right, how would I draw equipotential surfaces here? Well, if I'm really close to the charge, right, what we said is these field lines come out radially as long as I'm really, really close to this charge, and it doesn't feel the influence of this charge. And so really close, I get equipotential lines that are very similar to what I would get if I just had one charge. But as I get farther away and I start to feel the influence of this guy, my lines start to shift, so my equipotential surfaces have to shift. Usually the way I do it is I come in and I figure out about where I'm going to draw the line, and then I draw the parallel, and then I do the best I can. This is not a graphic design class. I'm definitely not an artist, but we can make a good effort, right? I think that might have gotten that kind of messed up. Right. This really should kind of look the same. The problem is not the physics, the problem is my art. But you can kind of see what's happening here. If I draw in these lines, and I'm doing my best to make them perpendicular. I'm not doing it very well, but that's okay. As long as I can kind of see what I mean, and you can kind of see what I mean, and more importantly, I can kind of see what you mean. And you might notice that right here in the center is this line that comes right down. This would be, of course, the point where the fields are right in between the positive and negative charges. But those are equipotential lines or equipotential surfaces. Again, it's just a graphic way for you to visualize what's going on with the potential, how the potential changes in space, and just it's based on the electric field. But more importantly, I've drawn this where I drew the electric field because I knew what it was, and then I drew in the potential. Now, in real life, that's a little bit backwards because, as it turns out, the electric field is really hard to measure. But the electric potential turns out to be pretty easy to measure. You can do it with a simple multimeter you can buy at Walmart. Which is why we honestly really care a whole lot about the potential anyway. It's because it's easy for us to measure. And so usually how this proceeds is I would take an actual system and measure the potential at different places and map out the equipotential lines and then draw in the electric field. In this system, I just know what the electric field looks like, so I'm using it as an illustration. But usually in real life, we go the other way. We measure the potential, and then that enables us to get the field. All right.